One of the most frustrating parts about working in a statically typed language is interacting with data from the outside world. Since this data doesn't originate in your nice little sanctuary of typed goodness, you can't guarantee it conforms to the shape or structure you might need for your application. In dynamically typed languages, all data is gooey and amorphous anyway, so it doesn't really matter. But static typing enthusiasts want stronger guarantees than that, and the only way to get those guarantees is to thoroughly check that all incoming data looks exactly how you want it to look. The same challenge exists in every statically typed language, including Gleam. But Gleam has something that some of those other languages don't, and that's an extremely nice package for dealing with dynamic data and checking that it matches the type we expect. This video is going to go through all the things you need to know about using the dynamic decode package in Gleam, from first principles all the way up to writing your own fully custom decoders. Let's get decoding. Installing the dynamic decode module is as simple as doing nothing. It's part of the Gleam standard lib package, so unless you've removed that from your project for some reason, you'll already have it installed. The decode module provides the decoder type and a handful of functions for constructing and using decoders. Decoders are then, in turn, used to validate data with an unknown type, represented in Gleam using the dynamic type from the standard library's dynamic module, returning a statically typed result. You won't often be running decoders yourself. We'll talk about using them with other packages later, but running a decoder is easy. You simply pass your dynamic data along with your decoder into the decode.run function. This will return a result that either contains your data statically typed, if the decoding was successful, or a list of decode errors describing what went wrong during the decoding process. Simple, right? So let's take a look at some decoders. The decode module contains a number of built-in decoders for primitive types, which are decode.string, int, float, bool, and bit array. You'll use these directly when you want to decode one of their respective types, or you can combine them. Wrap a decoder with decode.list to create a decoder for a homogeneous list of that type. Use decode.dict with two decoder arguments, one for the key and the value, to create a dictionary decoder, or choose decode.optional when your field might be a null value. Importantly, the decode.optional decoder can handle all common runtime representations of missing data, such as the null and undefined atoms on the Erlang target and null or undefined in JavaScript, and it will decode to a Gleam option type. So far, the decoders we've looked at have been good if you need all the values in the dynamic data you've been provided. But what if you're expecting an object but only really care about one value from within? Or maybe you just need the first item from a JSON tuple. That's where the decode.at function comes into play. This is used for extracting a single value contained within key value containers or array-like containers, including JavaScript arrays, objects and maps, or Erlang tuples. The decode.at function accepts a path to the value you're trying to extract from within the object, and the decoder you want to use on that value. The path is a Gleam list of integers or strings. I like to think of it as a JSON path. The strings represent keys in key value structures, and the integers represent indexes in array-likes. For example, you could use two strings to get a value from a nested JSON object, or you could use two ints to get a value from a nested JSON array. You can't, however, mix and match, as Gleam lists can only contain one type. If there's a possibility that a value won't exist at a given path, you can use decode.optionally@, which will wrap the decoded value in an option, returning none if the path wasn't present. So far, everything we've talked about has allowed us to create decoders for types that already exist. But what about if we want to decode dynamic data into our own types, like enums or records? In that case, we can write our own decoders. As a heads up, the API for creating custom decoders makes heavy use of Gleam's use keyword. You don't need to fully understand it to be able to write decoders. You can follow along and adapt the examples in this video, but if you want to dive a little deeper, my video on use will be linked in the description and in the top right corner of your screen. Let's start by looking at a simple case, enums. Here, we have an enum representing a subset of Pokemon types. If we were representing this in, say, JSON, we'd probably just use a string. However, in Gleam, we like type safety, so using an enum like this is definitely preferred. So, if we have some dynamic data, how can we check if it's a valid Pokemon type? If we already had a string, we'd probably use a case statement to do something like this. However, we actually have dynamic data, so we first need to check if we actually have a string before we can check the contents of the string. Remember, dynamic data could be anything. We do this using the decode.then function, which allows us to run one decoder after another. In this case, we want to run our custom type decoder after we run the string decoder. We'll start creating our decoder by declaring a block and using decode.then with the use keyword, passing in the string decoder as our argument. Now, we can use our case statement from earlier to check the value of the string and return the right Pokemon type. You'll notice that instead of just returning the correct Pokemon type variant, we return the result of decode.success. This makes the block evaluate to a decoder, which we can then use with decode.run. Instead of panicking, the failure case now returns a decode.failure with a Pokemon type value and the string Pokemon type. This seems a little bit strange, but the first argument is what's called a zero value, and we'll get more into what that means later. The second argument just makes it easier to see which part of your decoder has failed. Is it that the data is not a valid string, or is it just not a valid type? Speaking of being able to see where you failed, I'd like to introduce this video's sponsor, me. Well, my company Rover anyway. Rover is a code reliability platform that helps you ship fast while breaking nothing. We've recently released our PR reviewer feature that not only looks at your PR diff, but scans your entire application, alerting you to any risks or potential bugs. We've caught a few issues ourselves in our own codebase. It does this by turning your codebase into a graph, which we actually make available to you. You can explore or query the graph, or if you need to find something specific, you can use our chat feature to dig deeper into any connected codebase. Rover PR alerting supports any programming language, and we can create searchable graphs for JavaScript, TypeScript, and Python. Gleam, Go, Rust, and Dart support is also coming soon to the Rover graph. Check it out by visiting getrover.com or checking out the link in the description. The free tier includes more than enough usage for a single developer or a small team, so please give it a go and let me know how you get on. Your feedback is really appreciated and we'd love to hear it. Now, let's get back to decoders. Cool, so creating a decoder for an enum is fairly straightforward, but what about other custom types like records? Let's say we had a type for NPCs, or non-player characters, in a Pokemon game, starting with gym leaders. Our gym leaders have a name, a location coordinate, a type they specialize in, and an optional TM reward if our player successfully beats them, represented by the TM's number. We'll say that our dynamic data is JSON data in this format. We'll start as we did before, creating a block scope so we can use to create our decoder. Then, to get the values out of a record like a JavaScript object or map, or an Erlang map or array, we can use the decode.field function. This takes the field name and the decoder you'd like to use to decode that data. Like decode.at, decode.field can take a field name or an index if you want to get a value from an array. To get our location data, we have a couple of options. The best thing to do is to create a custom decoder for a two-element tuple and then pass that to decode.field. But for the sake of example, and for the sake of example only, we could use decode.subfield, which works very similarly to decode.at, except you can use it in custom decoders more easily. Decode.subfield works best when you only care about a single deeply nested value. To get our speciality value, we can use decode.field with the custom decoder for a Pokemon type we created earlier. Finally, we can get our optional TM reward value using decode.optionalField. This will return a default value if the field isn't present, and we can combine it with decode.optional to not only handle a missing TM reward field, but also handle it being null. Now we can just return decode.success with our gym leader value. And now we have a decoder that'll successfully decode gym leader NPCs. Great, but of course, Pokemon games have more than one type of NPC, and we need to include the most important NPC in any Pokemon game, the Professor. Let's add that to our type. When it comes to dealing with records with variants, the strategy you employ will depend on the structure of the incoming data. This is called a type union, meaning your type can be one of a number of variants, and unions are either tagged or untagged. As an example, an untagged union for our Pokemon NPC type above would basically look exactly like the Gleam representation. In this case, you'll want to use the decode.oneof function. This creates a decoder that runs through multiple decoders in sequence until one matches. Let's imagine we've already created our Professor decoder. Our overall Pokemon NPC decoder would look something like this. It's worth noting that all the decoders have to return the same type, even if they return different variants. You'll also want to make sure that you list your decoders in order, of most to least specific. Consider the case where we add a non-trainer NPC variant to our type that just has a name field. It's like the catch-all for normal people wandering around in the Pokemon universe. If we put the non-trainer NPC decoder before any other decoder in decode.one, every valid NPC would be classified as a non-trainer because all our variants have names and would therefore succeed the decoder. Unfortunately, we don't always have control over the shape of incoming data, so dealing with unions may be a necessity. Thankfully, some API creators are nice and will represent data as a tagged union. In this case, all variants will share a field that tells you which variant the data is supposed to represent. For our NPC type, we might see something like this, where we have a type string field. This makes our job much easier, since we can just extract the type field, then match on its value to return the correct decoder. This way, it doesn't matter what order we have in our decoders, because we can choose the right one based on the type field. You'll have noticed in the last example that we passed a professor value with empty strings for name and home into the decode.failure function. As I mentioned earlier, this is called a zero value. Zero values are effectively default values that decoders return if they fail, which allows the rest of any parent decoders to continue, collecting all the errors instead of just stopping at the first one. Consider our gym leader decoder one more time. We might get some dynamic data from an API that's not only missing the name field, but has an invalid value for the speciality field. Because the decode.string decoder returns an empty string as the zero value instead of just failing immediately, the decoder can continue to run rather than stopping at the first error. This gives us the following error message, which is far more useful than just telling us the name field is missing. The first argument to each decode error is the decoder that failed. The second is what type of value is present, and the last is the decoder we were checking at the time. This is all well and good, but what if you need a decoder for a non-Gleam primitive type, like an Erlang atom or a JavaScript date? For this, you can use new primitive decoder. This takes the name of the type you're trying to decode to, as well as a function that takes some dynamic data and returns a result. To avoid having to show you an example that dips into Erlang or JavaScript, here's how you'd re-implement decode.string with decode.string. The result either contains the string value in the OK case or a zero value in the error case. Of course, you'd usually use FFI or foreign function interfaces to do some checking logic in Erlang or JavaScript. And I've got a video all about that too. Check it out in the description or on your screen right now. The decode module also contains a few utility functions to make it easier for you to write decoders. Decode.map will allow you to create a new decoder by applying a transformation to the value of a previous decoder. This is useful with decode.one when you're decoding some dynamic data that might be a bit more loosely typed, like YAML, allowing you to convert everything into a single Gleam type. Decode.map errors will let you apply a function to errors returned by your decoder, or you could use decode.collapse errors to replace a list of errors with a single one. Again, this is useful with one of, allowing you to simplify the error that gets returned to your user. Although most of the examples in this video have been used with decode.run, that's not how you'll be using your decoders most of the time. Usually, you'll need decoders when interacting with a library that needs to deal with data of an unknown shape. Let me show you what I mean. If you want to deal with JSON, then you'll be using the Gleam JSON library. The JSON.parse function, which is what you'll be using to, well, parse JSON strings, takes in your JSON string and a decoder, returning a result of your statically typed data or a JSON.decode error. Interacting with Postgres, you're probably using the POG library, which takes the decoder for the rows returned by your query. All this said, the chances of you having to write your own decoder are actually reasonably low. It's not that you won't need decoders for your types. On the contrary, you probably will. It's that you'll probably use a tool that creates them for you. The Gleam language server has a built-in code action for generating decoders from custom types. How you activate this will depend a little bit on your editor, but if you display code actions while hovering a custom type, you'll see an option to generate dynamic decoder, which will do most of the work for you. It's still useful to have an understanding of how it's working though, as you may need to provide your own zero value or tweak the decoder based on the shape of your incoming data. There are other ways to generate decoders too. The Squirrel library, for example, converts your Postgres queries into Gleam functions and types, and includes decoders for all of your queries, completely custom every time. And that's it. You've just learned basically everything you need to know about how to use decoders in Gleam. What are your favorite decoder tips and tricks? What might I have missed? Let me know down in the comments. In the meantime, why not check out my video on the library I just mentioned, Squirrel? It's the best way to work with Postgres in Gleam. That video is on the left of your screen, but YouTube reckons the one on the right will suit you a little bit better. I won't be offended either way.